Let me introduce to you
Yeah,
Fabiana.
sure.
She's from the University of Bologna in Italy, in Bologna itself. And it's at about 8 o'clock in the evening, so it's quite reasonable, unlike some
Yes.
who are in Australia or in um, Africa. And this will be an example of doing things in the small, microbial, but having big impressions on
Yes.
okay, so Fabiana, I'll give you a 5-minute warning towards the end and take it away.
Okay, thank you very much for your presentation. And thank you very much also for the the job that you are doing in this in a SIMIODE, because for me is something new. It's the first time for me. Although I follow your work from since a few years ago, and it's always been my idea to communicate and to put students directly in contact with problems. And what I'm saying today is just an experiment in my last semester. And so in this last semester, I teach mainly differential equations. And I wanted to give my students the opportunity to see and to treat a model which is important in real applications. And one of the model that I chose, it is from a microbial interaction. So what I want to do now is to show a few results, and to show also how I structure the assignment and the result that I had from the class and from the students. So mainly, first of all, this is an idea of a project for a master in science in mathematics. So students are quite clever about the theory, and they are graduates, so they know the theory and they know how to treat theoretical aspects, but they need to become more aware of how these models can be used in practical applications. And so in my course is mainly on numerical methods. So what I teach them is the numerical solution of these problems. But I have to point out that the program where I teach is an international program. So I have students from mainly all over the Europe, mainly not from outside Europe, but actually they can and they like to work in groups. The course is in English, and they interact with foreign students. Second, each lecture consists of a theoretical part and laboratory part. And during this laboratory part, students learn how to implement these numerical methods. But usually in let's say in standard teaching, we give them simple models that we use for illustrate theory, and then they apply them and study the algorithm, study the programming on them. What I wanted to do this year is something different. So besides the implementation of such method using MATLAB, I wanted to give them the opportunity to just use directly the models from scientific papers. So I, instead of somehow circumscribe the topic as I used to do in the past. In the past, I used models, but I circumscribed them for the specific skill that I wanted to point out in the projects. Now I gave them just a scientific paper, usually recent, but I gave them 2 or 3 scientific papers. I chose one for this topic, but for this talk today, but they did other groups developed other topics. And I wanted to see how they managed this situation in which they had to understand the model, they had to understand the problem, to read the paper, and to come up with the equation, and apply what we are learning in the course, which is not only the solution of ordinary differential equation, but also some principle of modeling in the sense of identification of parameters. So they have to develop their code and to see how to study this and how to apply the methods that they had studied into this specific problem. So the project that I gave, the assignment that they had was to use this paper. This is a recent paper. You see that it's of 2022, where they illustrate a new approach for a mathematical model of a killer-sensitive interaction in a particular condition applied to the transition from must to wine. So the topic, they were very interested in the topic, so they liked all the physical also and chemistry illustration in the paper. But they immediately realized that it was not easy at all to reproduce what was written in the paper, and this was one of the problems that they had at the beginning. And this problem was such that they had to go to the references, find references that were where this model was originated, and they had to develop some practice in this topic. What was asked in the project was to analyze the forward problem, so build the differential equation from the paper or from the papers as they did. The initial value problem, build the initial value problem. And once the analysis of the forward problem and the choice of the best numerical solvers, the analysis of stiffness, for example, the characteristic of stiffness of this problem was done, then they simply had to implement the Gauss-Newton code. And basically, we went into detail about the Gauss-Newton approach. So they had to write this approach in detail and compare with the given MATLAB optimizer functions. And then there was also a final topic, which was to use this model to derive an experiment in boundary value problem, but it is not what I have no time to talk about this in this evening. But actually, it was a part of the project. Let us start as we develop. This is mainly the text of the part of the code that they had to generate. They had to use to understand the model parameters, and they had to discuss the stiffness of the problem and report the efficiency of the MATLAB solver. And I have to say here that they used built-in solvers, but they had also implemented mainly implicit Runge-Kutta solvers. So they had to implement, and they had to test the efficiency of their solvers. And then it was asked them to generate a data set, so build up something which is an artificial data set, a synthetic data set from the given parameters, and then propose try to do some experiment in parameter estimation. And we will see that this model is quite complex, and the fact that they were not able at the end to estimate all the parameters, they had to estimate one parameter at a time. And this was part of the difficult things that they had to face during their project. So let us see something about the problem. The problem is an example of microbial interaction. In microbial interaction, in wine fermentation, there are a wide varieties of yeasts. Some of these yeasts produce negative changes in that cause damage and economic losses to the product. There are some artificial products, sulfur dioxide, that can be used to control spoilage, but this harms human health. So what is proposed in this paper and in the other paper originated from in this approach is to use a biocontrol, which means that some different type of yeasts is introduced in the product in such a way that they kill only the spoilage and the sensitive yeasts without damaging the whole the human health. So basically, we have two populations of viable sensitive and viable killer populations. Then the model is the description of the interaction of these two populations and all other type of substances that are connected with this process. And actually, from a mathematical point of view, the idea is that if we build a good mathematical model, that we can predict the behavior of the killer yeasts, and moreover, we have to define to find which is the optimal quantity of killer yeasts that we need to control the spoilage yeasts in the smallest possible time without introducing the minimum quantity of killers in order to get a control and to kill the spoilage yeasts. And so, in this model, there is also the need to control and to explain the kinetic parameters that are used in this model. And as I told you, there was a need to see other two papers that were involved, where these dynamics were described in a more clear way, even if it was not, the experiments were not applied to wine, but they were applied to other liquids. Anyway, students found these papers, and at the end, they came up with the model that was described mainly on this Pommier and other paper, older paper. So the model consists at the end of a system of six ordinary differential equations, which allows to study the interaction of two yeasts, and one is the spoilage yeast, and the other is the biocontroller or killer yeasts. So the six population control the number of viable killer and sensitive cells, and the opposite, the cumulative killer deaths and the cumulative sensitive deaths. And then there are other two populations that are the toxin concentration and the inhibitor of both cells. There is a population that is actually affected by the dynamics of both populations. So at the end, these are the equations that are necessary to describe this process. And basically, the evolution in time is explained by the difference between the rates in killer growth and the sensitive growth. So we have the rate of the viable killer and growth and death, the same for the sensitive. And then we have these two populations, these two related to the sensitive to the sensitive killer and sensitive rate populations. And then there is the behavior of the toxin, which is related to part which is actually as a production, and part is somehow dispersed in the adhesion to the cells. And then we have the inhibitor rates. So at the end, this is the final type of equation that they were able to analyze and solve. As you can see, the expression of these dynamics is quite complex because it takes into account many parameters and many equations. So I won't define them into detail. What is interesting here is that you find parameters and the constants that I explain now. There are some constants that are related to the substance, and somehow they can be acquired, they can be measured by different analytic procedures, while there are actually quantities that need to be modeled by using the dynamic model, the parameter estimation process. And mainly it is the natural death, killer, and sensitive yeast. Mainly this parameter is the most important, as well as the toxin cause death rates and the specific toxicity of the toxin, for example. These are the main parameters of this model, while the other constants are taken equal to 1 for these experiments. But of course, in changing the substance and changing the elements, it is necessary to take into account also of these elements. So as you can see, if you want to actually treat all of these as parameters, it is almost impossible to get an estimate of all these parameters. But even if we take them constant and we consider only, for example, the estimation of a single parameter, we will see that we have some problem. And this is mainly what I wanted to show this evening. So now we obtain our differential model. So we collapse everything together and we have this, this set of 6 equations. The initial values are defined in terms of the global population of viable sensitive, and here you see there are 3 million of viable sensitive cells. This is a standard number used in the papers. And then we consider that only one part of this killer viable sensitive is the number of initial killer. And so this accounts for the introduction of a portion of killer and see how this portion of killer acts in the dynamic of the population. And all the other population are equal to 0. The time interval in this case is 30 hours. And this is mainly the experiment that is we found in this paper, and it is quite different from the starting one, but we had there was some problem at the beginning. So the first observation is just how the solution looks like if we change the initial value of the ratio between the killer and the sensitive. This is a quite high ratio, and we see a quite fast dynamics. We see that the population of the killer reaches its maximum after 5 or 6 days. And after, say, 10 days, we almost have the population of viable sensitive that. One thing that is to appreciate is the ranges of this variable, which is on 10 to the 6, and it will be a problem, and we will see how we had to manage to this problem. And the other one is that the other 2 populations, T and I, are on different scales. So we have part of the population that are on the scales on 10 to the 6, and the other part which is on a much smaller scale, and therefore they are represented in this way. If we decrease the number of initial values of initial cells, then what we observe is that the dynamics is slower. So we have a slower increase, and which happens only after the maximum happens only at the 15 days. And we see that the finish, somehow the death of all the cells is finishes at this point. You observe that now the dynamics does not reach the end. This is one of the problems that has become we encountered in this model. So let us first see what is the forward model. The forward model is the ordinary differential system of differential equations, which is written in the standard way. And first of all, a very fast analysis of the linearized problem, just to see how in the initial point and if the problem is stable and if it is stiff. So what it's been observed is that evaluating the Jacobian in the starting point, we have that all the eigenvalue are, we have that we have a very small eigenvalue of the order of 10 to the 5 and doesn't change if we change the initial conditions, and this gives us the idea that this problem is very stiff. Second, we see that there is only one actually eigenvalue which is a real part, which is larger than positive. So actually there is also a mild instability, even if it is not a problem because we don't have a long time evolution. But actually this problem is stiff, surely, and shows a mild instability. This is what, of course, now students we developed many older methods for MATLAB methods for stiff problems, and this is the standard behavior. Just to try, we can see that if we use a solver which is not suitable for stiff problems, you see the number, the enormous number of function evaluation that we obtain, of course. And they tried also their own methods, even if their own method was based on fixed steps. So they used the same step used by MATLAB solvers, and they obtained very good solution. But of course, the number of function evaluation in this case was very high. But remember that now we have 4 and 3 order methods. So actually these methods are very accurate, and they could be suitably used in a context of parameter estimation. So this is the part of the analysis of the forward problem. Then we have the analysis of the, we have an experiment for the estimation test. So we define the example that I showed this evening is just to estimate one parameter, and this parameter is the death spoilage speed parameter. And so we rate, this is a rate. So we set a reference value, which is exactly the value that we had in the given parameter. We solve the forward problem, we obtain data, and then we simulate measurements. So we take from this equation just a few points. Here you see empty points, and the example that we see this evening is only on 10 points, but of course the idea is to study what happens if we change the number of points, and also the position of the number of points. And so we obtain data, we measure, and the only population that we can measure are the variable killer and variable sensitive. So we measure only the Y1 and Y2 components. The other components cannot be measured. So we consider data that come from the first two populations that are measured in using these values. And so we relate, we obtain our data by measuring and the solution of our differential equation that is named also state equation in this context. Then we add the noise. Usually it's random from normal distribution in such a way that we control the relative error. And so we select this value, we try different values. And the main idea is to see how and if this parameter can be estimated. So, okay, these are data, an example of data with delta 10 to the minus 2 with m equal to 10. And this is just an example. Consider that this is on the scale of 10 to the 6. So it is quite a large perturbation, even if they seem very close. And so this is the parameter identification problem, the classical least square minimization. And we know that if we want to solve this problem, we have iterative method, and we need to start from we need a starting guess. And mainly in this problem, the starting guess is the problem. So what I will show you is, for example, the problem of defining how far can I be from the true solution in order to still be able to to get a good estimate of the final parameter. So in this case, since this is a test problem, we can evaluate the parameter relative error, and we can measure it.
Fabiana, we're doing fine. We have about 5 minutes. Okay, go ahead.
Okay, I finished. I will be very, very fast. Okay, and so the application was, the problem was to apply the Gauss-Newton method and see what happens at the end. So let us see the first, okay, I skip over how we had to manage the gradient computation for the implementation of the Gauss-Newton method, and it was done using the sensitive approach, so the sensitivity matrix approach. And so they built up also the sensitivity equations, and they solved an augmented system introducing the sensitivity equation. And so, for example, in this case, this is one case. We assume that the initial value is the reference value plus or minus an error, maybe. And we want to see how far we can go in order to obtain a relative error which is of the order of 10%. So in the case of small noise, small amount of noise, we see that this parameter is very, very good in the sense that we can use a very huge, far away initial value, and we still obtain a very good value. And of course, when we are very far from the good solution, we increase the number of function evaluation, and this is one of the results. The second one is that if we want to increase the number of the amount of noise, we have no hope to obtain an estimate of the parameter unless we scale data. So we have to apply a scaling of data in order to be able to obtain results that are comparable to what happens for a small noise. And this was one of the issues that we had for this problem. So I just conclude just saying that I was amazed by the enthusiasm of the students for the reading of the scientific paper, and for also all the problems that they found and how they try to come up with their difficulties, and they appreciated much to see that the methods and the numerical methods, but also the mathematics that they studied, had such an impact in practical and in real life, and to explain and modeling natural phenomena. They appreciate the fact that they had to build test problems, because once you want to appreciate your model, you have to see if you are able to solve and to define the quality of the model that you are preparing, because there are models that you have to see if the parameters that you want to estimate are possible, if it is possible to estimate this parameter, if the characteristic of your model. From the point of view of my point of view of the teacher, surely this is an approach which is more costly from the point of view of the interaction, and also in the idea of be able to solve small problems that we can encounter during this phase. But at the end, it is much more. I get much more satisfaction, because I see that students go beyond what you teach, and they try to apply, to give their own solution to something that you have not taught, you have not taught, you have not tell them. And this, I think, is a great value. So thank you again.
Did the original papers have sufficient data that you could estimate some of the parameters, or only when you were generating the parameters?
They were not sufficient, and the main problem was that the parameter that they gave in the paper actually produced curves that were much different from what was obtained there. What was shown. They didn't have any additional materials, and so we resort to another paper, the older paper. And in that case, yes, for the model, the specific model that I am using, yes, in that case, we were able to reproduce the data, but we were not able to get the observation. There was not additional materials, and of course, we didn't have time to ask authors and so on. I think it's beyond the scope and the purpose of this type of projects in this sense.
This was a group of master's level students, correct?
Yes.
Have you done any parameter estimation in earlier courses, in undergraduate courses?
No. And I haven't, and I have to say that in our curriculum it is not.
There's no room.
No, because the undergraduate usually the courses are very theoretical, and so they are not involved in this type of problems.
Well, I must say, it was fascinating technical work. I was terribly disappointed. I thought you would have a video of your students out in the Italian countryside stomping grapes and singing Italian, but we look at your gracious offering to us. And the references, of course, are in the presentation, and they will. Well, thank you very much, Fabiana. And
thank you.